Let's go ahead and bring up our classroom here. So we are at the end of week 6 of class, which means that after tonight, we're only going to have 3 more IPC classes together, if you can believe it. So the specific type of measurement that I was talking about that we're going to go over today is called density. How dense is a certain piece of matter? So you may have heard of the term density or something being dense before. And in your head, when you think about things that are high in density, you might think about things that are really big or things that are really heavy. And that's kind of related to it, but those, just how big something is or how heavy something is, doesn't really tell the whole story. Instead, density is what we can call the measure of compactness of a material. How compact, how tight together are the atoms and molecules in this substance? So the closer together, the more substance that we can fit in a certain area, the higher the density of that substance. The more compact our material, the more dense it will be. So density is not just heaviness. You might think, oh, a really dense object or a really heavy object has to be really dense. Not necessarily. Density also involves how much space an object takes up. So just because an object is really big and really heavy doesn't necessarily mean that the object is dense. Instead, density is a combination of both heaviness and volume together. All substances have density. So liquids and solids, it's pretty easy to see and kind of experience, but gases have density as well. And then a little bit later, we'll talk about how having gases of different density can change how they interact with each other. So the way that I like to think about density and the way that I always kind of imagine it is, imagine you have like your kitchen trash can at home, right? As the trash starts to get closer and closer to the top of the trash can, do you just immediately empty it out as soon as it looks full? No. If you're like most people, you smush it down and you keep smushing your trash in there until no more can fit, until it is completely full. So as you are smushing down that trash, you are compacting all of those papers and food scraps and napkins and paper towels and stuff. You're compressing that all into the trash can. So the trash can is staying the same size, right? It's just a plastic shell with a bag in it. But you're adding more and more and more and more trash in there. And you're squishing down the old trash in order to make room for the new trash. When you do that, you're increasing the density of your trash. You're increasing how compact your trash is. You're fitting more and more trash into the same size space. So we can think about it as particles or atoms. We can think about it as trash, but the same concept applies. When you're more spread out, you're less compact. You have stuff that's kind of full size. It's still got its shape originally. Then you are less dense. But if you squeeze everything together, if you force all those atoms and particles close into one another, if you push down on that trash and you're fitting in more and more trash, you're making those particles, you're making that trash more compact, more dense, more of it in the same spot. So that's what we mean by density. It's not just how heavy something is. It's this combination of heaviness and the amount of space that it takes up, its overall volume. So like a refrigerator, right? Very, very heavy, very, very big. So you might think that a refrigerator would be pretty dense. But an empty refrigerator, like imagine one that's like on display at Home Depot or Best Buy or something. An empty refrigerator has a whole bunch of nothing in the middle, right? Maybe there's some shelves in there, but that's it. Otherwise, it's just open space. So just because a fridge is really big and heavy doesn't necessarily mean that the fridge is dense. It has a lot of this less compact open space on the inside. Now, you can make it more dense by filling it up with meat and cheese and leftovers and condiments and pickles and vegetables and fruit and all sorts of the other stuff that you keep in your refrigerator. That's definitely going to start taking up space, filling up that area, and making everything more compact, more stuff in the same area. So again, density is all about this compactness. How much matter are you fitting into a certain space? So as you might be able to tell by the fact that I've talked about it a whole lot already, density is all about this ratio between the mass and the volume of an object. So mass we talked about yesterday, or on Tuesday, so like grams and kilograms and milligrams, stuff like that. And volume we talked about on Tuesday as well. That was our liters and milliliters and centimeters cubed and all sorts of fun life stuff like that. So we have our weight, our amount of matter, and we have our volume, our space that the matter takes up. So if you want to think about how changing the weight or changing the volume can adjust the density, if the volume stays the same, so say you have your plastic trash can, right? It's not getting bigger or smaller, it's the same size. But the mass increases, you put more and more and more and more trash in there. It gets heavier and heavier while it's the same size. The density will increase. You're making all that trash more compact. You're packing it really tightly in there. And so the density and the compactness is going up. On the other hand, if you then take your plastic trash bin and say you live in an apartment where you empty things into a dumpster. You walk out to the dumpster and you don't take the bag out or anything. You just dump everything directly into the dumpster. The mass is the same. You have the same amount of trash in your trash bin as is now in the big dumpster. But the volume went up. Dumpster has way more space than your trash can, right? So now all your stuff can just spread out across the bottom of the dumpster. It can take up all the space that it wants. Now our density has gone down. Our volume got way bigger, but our mass stayed the same. We have the same amount of stuff, but now it's in a way bigger place. It's not as compact, it's not as tight as before, so our density goes down. So density is related to mass and volume together. If the mass goes up, then as long as the volume stays put, the density will go up. If the mass goes down, the density will go down. If we keep the mass the same, if we have the same amount of stuff, if the volume goes up, if we put it in a bigger space, it'll be less dense. Or if the volume goes down, if we cram it into a smaller space, it'll be more dense. So again, it's not just weight or size, it's all about this combination, this ratio of mass and volume together. All right. Before we go on and talk about how to actually figure out and calculate density, does anybody have any questions so far? Anything about density or the trash example or anything that you're still a little confused or a little not clear on? right, doesn't sound like it. Sounds like most people are keeping up okay so far. So density, compactness, mass, and volume together. So because of this, scientists came up with a relatively simple equation to calculate density if we can measure the mass and the volume of an object. And that equation looks like this. It's in big font because it's an important equation. Density, D, is equal to mass divided by volume. Density is equal to the mass, the heaviness, divided by the volume, how much space that it takes up. Mass is usually represented in grams, and volume is usually represented either as centimeters cubed or milliliters. That's kind of the most common ones that you see. But density equals mass divided by volume. If you know what your mass is and you know what your volume is, then you can pretty easily calculate density.
What if you don't know the mass and you have to find it? How do you find the mass?
That is a great question. So if you have like a random object, like, I don't know, say my computer mouse right here. My computer mouse definitely has density, but I don't know all the stats about this computer mouse. So to find the mass of my mouse, I could put it on a scale, right? Like a kitchen scale or something like that, and put it on there and weigh it and see how many grams does my computer mouse weigh. Finding volume for something shaped kind of like this is a little bit trickier. One method you could do is you could fill up a measuring cup with water and then drop this in there and see how much higher the water goes. And that will tell you in milliliters what the volume of your object is. But regardless, you can relatively easily measure the mass and slightly less easily measure the volume and use that to figure out your density. So let's say, for example, that I measure the volume of this, I drop it in the water, and I measure that this guy has a volume of 50 milliliters. And I put it on my scale, and I measure that it has a mass of, let me kind of guess here, like 100 grams. So if my volume is around 50 milliliters or 50 centimeters cubed, and my mass is 100 grams, then what is the density of my computer mouse? Feel free to answer either out loud or in the chat as well. I can see that.
Repeat it again, sir.
If the volume of my computer mouse right here is 50 centimeter cubed, and the mass of my computer mouse is 100 grams, what is the density of
2.
my mouse? 2. Bingo.
It's 100 divided by 50.
Nailed it. That is exactly right. My volume was 50. My mass is 100. 100 grams divided by 50 centimeters cubed gives me 2 grams per centimeters cubed. So the density of my computer mouse in that example would be 2. So simple calculation, figure out your mass, figure out your volume, then all you have to do is mass divided by volume. So that's a really handy dandy little equation. But because it's so simple and easy to work with, we can also move some of these variables, move some of these numbers around in case we want to calculate something else. Like, I don't know, let's say volume. If density is mass divided by volume, m over v, then volume, if I know what my mass and I know what the density is already, I can figure out the volume. So for example, if I knew that the mass of my computer mouse was 100 grams, and I knew that the density was 2, then I could calculate the volume of my computer mouse to be 50. Similarly, we can also calculate the mass of something if we know the density and the volume. This guy is a little bit different. Instead of dividing like we do in our density and volume equations, for figuring out mass, we multiply. So if you know that the density is 2 and you know that the volume is 50, you can do 2 times 50, and that'll tell you that my computer mouse has a mass of 100 grams. So no matter what two numbers that you have, as long as out of density, mass, and volume, you have 2 of those numbers, you can do a simple equation to figure out the third one. If you know the mass and you know the volume, you can calculate density. If you know the mass and you know the density, you can calculate volume. If you know the density and you know the volume, you can calculate mass. Some people also like to use what's called the DMV triangle, which is this weird looking guy right here. And the way it works is that you make a triangle and you put M in the top corner, D in the bottom corner, and V in the other bottom corner. And depending on the value you are looking for, you see how the other two are aligned. So for example, if I want to know the density, I can look at this and essentially cover up density and see, all right, to get density, I have M and V, and on the triangle, M is above V, so that means I'm going to divide. I'm going to do M divided by V. Similarly, if you want to know the volume, you cover up the V and say, all right, I have M and D, mass and density. The triangle says mass goes above density, so I'm going to do M divided by D in order to find the volume. Finally, if you want to know the mass, you can cover up the M and say, all right, my triangle says that D and V are next to each other. And when that happens, I multiply. So mass is equal to D times V. So setting up this little triangle can help you to remember, if I want to know one of these, I look to the other two, and based on how they are positioned, I can figure out the equation that I need. So again, density equals mass divided by volume. That's our basic density equation that we were just talking about. But if we want to know the volume, we can just as easily do mass divided by density. And if we want to know the mass, we can just as easily do density times volume. All right, so knowing these three guys is pretty important. Your assignment for today and on Monday is based around it. So does anybody have any questions, anything about our density, volume, mass equations that you're still a little confused on?
No, sir.
Right, cool. Sounds good. So again, as long as you know 2 of the 3 values, you can do a calculation to find the third one. The calculation that you do depends on what you have. If you know the mass and volume, you can divide to get the density. If you know the mass and density, you can divide to get the volume. And finally, if you know the density and the volume, you can multiply to get the mass. So that is how you calculate density, or one of the other measurements, based on the types of information about the object that you have. So for the next part of class, we're going to kind of talk about how the density of different objects differs, and what happens when objects of different densities interact with each other. So for example, I mentioned earlier that gases, even though they're invisible and they feel like air and we can't see them, they still have density. And one of the interesting things about gases relates back to something that we talked way long ago about in like that first or second week of class. So you may remember the term kinetic energy. Kinetic is all about motion. And this is what we were talking about when we were talking about solids, liquids, and gases have the particles that are always in movement, and how much movement the particles are doing is called their kinetic energy. The other thing that you may remember about kinetic energy is that it is directly linked with temperature. As the temperature of an object goes up, the particles move faster and faster, and that object has more kinetic energy. So the interesting thing about gases is that when their kinetic energy goes up, when they get hotter, the gases tend to expand. So the particles are moving faster and faster, so they're moving farther away from each other. And that means our volume gets bigger. And as we were just talking about, when our volume goes up, the density tends to go down. So the greater the volume, the less dense the gas. So the hotter that the gas gets, the more volume that it has, and the less dense that it becomes. So that's why cold air is more dense than warm air. So if you've ever been in like a house or something, like a 2-story house or on the second floor of an apartment building, the first floor tends to be colder than the second floor because cool air tends to sink and warm air rises up. That's also the principle behind why hot air balloons work. So the reason why hot air balloons are able to drift through the sky is not because they're getting pumped full of some lighter than air gas like helium or hydrogen, but it's because they have that big tube in the middle that's like a furnace. So when they want to go up, they turn it on and a whole bunch of fire comes out. And when that happens, the air inside the balloon gets hot, but the air around it is cool. So the hot air inside the balloon is less dense, so it starts to float and try to go up above the cooler air that is surrounding it. So that's why hot air balloons are able to lift off the ground, is because gases, when they get hotter, they become less dense. And less dense objects and matter tends to float, while more dense matter tends to sink. A very similar thing actually happens with liquids as well. Colder water tends to sink, and warmer water tends to rise to the top. Liquids can also separate themselves out from other liquids based on density. So like here we have something that looks like motor oil on the bottom, and then like some cooking oil or vegetable oil or something on top. And then maybe like, I can't tell, maybe like some vinegar or some other clear liquid here in the middle. So these three liquids are at three different densities, which is why they aren't really mixing with each other. The most dense liquid is on the bottom, sinks all the way down. The least dense liquid rises up to the top, and then the liquid with the middle density ends up sandwiched in between the two. So if liquids of different densities are mixed together, eventually they have a tendency to separate out at their densities. You can also change the density of a liquid by adding stuff to it. The more stuff that you dissolve in a solution, the more dense it becomes. So this is why ocean water is more dense than fresh water. If you've ever been to the ocean, it's a little bit easier to float on the ocean than on the water in a lake or a pool or something like that. And that's because all of the salt that's dissolved in the ocean adds to the density, adds to the compactness of all the salt and the water molecules all swirling around one another. So that makes ocean water and salty water more dense than fresh water. So this density regarding how things sink or float or interact with each other is true even if you have solids and liquids that are mixing together. So a pretty cool example of this is that mercury has a pretty high density, 13,600 kilograms per meter. And so does lead, 11,340 kilograms per meter. So both these guys have a pretty high density. They're both relatively dense metals. Lead, like most metals, is a solid at room temperature. But mercury is very interesting. Mercury is one of the few metals that is a liquid at room temperature. The melting point of mercury is somewhere around like 50, 60 degrees Fahrenheit. So mercury is a metal, it's very dense, but it is usually a liquid at room temperature. So imagine that you have a lead ball and a glass, a beaker full of mercury. What do you think is going to happen if you take that lead ball and drop it into that glass of mercury? Do you think it's going to sink down to the bottom? Is it going to float on top? Or is it going to kind of hang out somewhere in the middle?
Sink to the bottom.
All right, I got sink to the bottom. Anybody else? Any other guesses?
I'd say float.
All right, we got one sink and one float. Anybody else? Feel free to chime in.
I think it'll sink.
Got some sink. All right. Anybody else? Any other guesses?
Sink.
All right. Another one for sink. Any other? Someone?
Sink.
Got another sink. Got another sink. All right. Cool. So the interesting thing about lead and mercury is that even though lead is a solid and mercury is a liquid, lead has a lower density than mercury. So lead's density 11,000 something, mercury is 13,000 something. And so because of that, a lead ball will actually float on liquid mercury. Even though these are two very dense, very heavy metals. Because lead as a substance is less dense than mercury as a substance, it doesn't matter what type of state that lead is in, solid, liquid, it's going to float on top of the mercury. Again, it's all because of these differences in density. Lead has a lower density, and so it floats on top. Mercury is more dense, it has a higher density, so it sinks down to the bottom, or in this case, it stays below the lead. So there's actually some really cool videos that you can find online of people making all sorts of different things float in liquid mercury because it is so incredibly dense. Like, for example, anvil, like the thing that you see in a blacksmith shop, or that you see cartoon characters like dropping on each other's heads in Looney Tunes and stuff like that. Anvils are used to bend and shape metal. They're usually made out of iron or something like that, and they are incredibly heavy. Even a fairly small anvil can be like 150, 200 pounds. But because it is made out of iron, iron is also less dense than liquid mercury. So there are videos you can find online of people that have a big tub of liquid mercury and they chuck this big anvil into it, and you see this incredibly heavy metal anvil just kind of floating around the surface of the liquid mercury. And again, it is all because of density. The mercury is more dense than the lead or the iron or other stuff that is lighter. If you could find something that had a higher density of mercury, I can't remember, I think gold is more dense than mercury. So like if you took a piece of gold or a gold bar and dropped it into this cup, it would sink down to the bottom because gold has a higher density than mercury. So the state of the object doesn't matter as much as its density when it comes to if it'll sink or float when combined with another object. In general, solids tend to be more dense than liquids and gases, which makes sense. The particles in a solid are more compact, more close together than most liquids or gases. But again, it depends on if you're dealing with different types of material, like the lead versus the mercury. But also, one intriguing compound that does not follow this rule, it has the opposite effect, is H2O, water. When water freezes, it actually becomes slightly less dense than liquid water. So ice, like the ice in your water bottle or soda glass, or the ice in an iceberg in the ocean, is slightly less dense than liquid water. So this is why, this is why ice cubes float in your drink. This is why lakes and ponds develop ice across the top of the pond and it doesn't sink down to the bottom. There's a complicated reason why that we're not super going to get into. Essentially, it has to do with the fact that when the water freezes and crystallizes, the particles line up in a way that physically spreads them out a little bit further than when they were liquid water. So usually, a solid of a material is more dense than the liquid of that material, but ice is a very intriguing example of the opposite case. So that's why even though this iceberg is huge and probably weighs thousands and thousands of tons, it's still able to float along at the surface of the water and not sink to the bottom. All because frozen water is slightly less dense than liquid water. So some other things that can affect density are temperature, like we already talked about. Liquids and gases tend to be less dense when they get hot and more dense when they get cold. Pressure can also affect density. So if any of you guys have like an Instant Pot or a pressure cooker or something like that at home, my wife and I got one for our wedding present a couple years ago when we got married. And we use it pretty consistently, like at least a couple times a month, we'll bring it out. And the way that pressure cookers work is that they heat up water and gas inside of them. And we already talked about how gas, when it gets hot, expands. But in a pressure cooker, everything is sealed off. That gas can't go anywhere. So instead, the gas gets faster and faster. It's bouncing all around the inside of that pressure cooker. And so instead of the density going down, the density actually goes up because the pressure is getting higher. You're getting more and more gas and water stuff moving around, but it has nowhere to go. It's all stuck in that area. And that increased pressure inside of the pressure cooker helps to cook the food in there faster. It helps the temperature of the food get up to the correct heat faster than if you did it in a traditional oven. And then another one that we already talked about was dissolving stuff in your liquid, like salt dissolved in water. So ocean water is more dense than fresh water. And there is actually even a type of water that is more dense than ocean water. There is a sea in the Eastern European, Middle East area of the world called the Dead Sea. It's called that because nothing lives in it. No plants or fish or insects or anything like that. And the reason that nothing lives in the Dead Sea is because everything, the water in there, is incredibly salty. There is a lot more salt dissolved in that water compared to traditional ocean water. Because of that, it is a very popular tourist destination, not just to go swimming and have fun, but also because you float super easily on the top of the sea. The water is so much more dense than normal water that you're basically bob up and down like a cork on the ocean on the Dead Sea. And that density is all thanks to the tons and tons of salt that is dissolved in the water, way more than traditional water. So the more salt concentration your water gets, the higher the density of your water. All right, so for the last thing that we're gonna do with our density stuff tonight, I have this table of some different substances and their densities laid out, including liquid water. And one of the cool things about liquid water is that it has a density of exactly 1.000000. So totally pure water has a density of exactly 1 gram per centimeter cubed is the density of pure water. So I have a couple different substances here, and I want you guys to help me figure out, excuse me, would this substance sink or float if you threw it into a pool of water? So first easy example that I'll do for you, air is obviously a very low density substance. It only has a density of 0.0013. So the density of air is way lower than the density of water. So if you ever mix air and water together and you get a whole bunch of bubbles, those bubbles are always going to float up to the top, right? If you've ever gone swimming and you've gone under the water and you breathe the bubbles out from your nose or your mouth, those bubbles that have air that came from your lungs always float directly to the surface of the water. The air is super low density compared to the water, so they'll start floating pretty much immediately. So I did that one for you guys, but I'm gonna have you guys help me out with some of these later ones. So let's say you take a piece of wood, like an oak branch or an oak leaf or something that you find next to this pond, and you chuck it in. Oak has a density of 0.85. So is a wood oak branch going to sink or float on water?
Float.
Float.
Float. Exactly. Wood is lower in density than water just by a little bit, but it's still enough to count. So wood 0.85 is lower than 1. So wood is also going to float on water. Like we talked about, ice has a similar density to water. Obviously, ice is just frozen water. Ice has a density of 0.93. So is a block of ice going to float or sink in water?
Float.
Yeah, float. Exactly. Like I was saying a little bit ago, ice is a teeny bit less dense than water. Ice, according to this chart, ice is 0.07 less dense than water. But again, that's still enough to be enough of a difference so that ice will float on the top of any water that it is put in. Good. All right, what about aluminum? If you take your soda can and you crunch it up into a ball and toss it into the lake, aluminum has a density of 2.7. So is aluminum going to sink or float in water?
Float.
Yep. I heard some sinks in there, and sink is correct. So aluminum's density is higher than water. 2.7 is a little bit bigger than 1. So aluminum, if you crunch it up, will sink if it goes in water. Now, I know some of you may have seen an aluminum can floating along the surface of a water before. That has to do more with the shape of the can. It acts kind of like a boat where it helps it sit on the surface. But if any water gets inside of the can, that'll cause it to start to sink because of the density of the aluminum. All right, what about lead? We've already talked about lead. Lead is pretty dense. Lead has a density of 11.3. So if you have a piece of lead and you drop it into water, is it going to sink or float?
Sink.
Precisely. 11.3 is a pretty dense material. Again, water only has a density of 1. So lead is going to sink straight to the bottom. Same thing with gold. Right? Gold has a very dense material. 19.3 grams per centimeter cubed is the density of gold. So that's why if you see like all the movies about shipwrecks and stuff and sinking to the bottom with all their treasure chests, that's why the gold sits down there at the bottom of the ocean, because gold is very dense and it's just going to sink straight down through the water. Some other interesting things that are a little bit less dense than water include some alcohols like ethanol, which is the alcohol in your sand sanitizer, and it's also the alcohol in the stuff that you drink, and methanol, which is an important alcohol for producing certain types of fuel. Both these guys are slightly less dense than water, so they both float on the top. The ethanol, this fact, is one of the reasons behind why they're able to do flaming shots at a bar. So if you've ever seen anybody order a flaming shot or a flaming drink, the way that they're able to do that is because ethanol, which again is the alcohol that you drink, floats on the top of water or things that are mixed with water or other types of mixers like you might have in a shot or a drink. So when they're getting ready to make a flaming shot, bartenders will pour a little bit of an extremely high alcohol drink like Everclear or Bacardi 151 or something like that. Just a tiny little amount right on the top. and that alcohol will sit right on the top of whatever shot or whatever drink that they have because of that low density. And then they're able to light it on fire because ethanol is also very flammable. So because of this slightly lower density than water, that's why we're able to make this alcohol layer on the top that we're able to set on fire for flaming drinks. So again, how different objects interact, whether or not they sink or float in each other, is all completely dependent on their density. Lower density objects tend to float to the top. Higher density objects or substances will sink to the bottom. All right. Does anybody have any more questions on what density is, how we calculate it, or how it's related to different types of objects?
So, I mean, I think you pretty much answered this earlier, but like if it's in a different liquid, does it change the density of what you put it in? Like say soda or tea or whatever.
Like, you mean if you mix two different liquids together?
Well, like will lead still float in like soda or milk or whatever liquid?
Probably, yeah. So most of those things are probably a little bit more dense than water. Because soda is essentially water that has sugar mixed into it, and milk is water that has a whole bunch of different proteins and fats and stuff in there. So those things are probably a little bit more dense than water. But I would say they're probably still not as dense as things like lead or gold. So in order to know exactly whether or not lead or aluminum would sink or float, you'd have to know what the density of the soda is or what the density of the milk is. So whether or not aluminum or lead or stuff like that sinks or floats does depend on the liquid that you put it in. And if the liquid still is a lower density, then the lead will sink. But in the case of the liquid mercury that we saw earlier that had a higher density, I think it's somewhere like right in here, it's around like 13.6 something. In that case, the lead floated because even though the mercury was liquid, it was still more dense than the lead. All right, good question. Any other questions, anything about density that you're still a little bit confused about or want to know more about? All righty. Like I was saying earlier, the main takeaway from the density notes for today is our density equations. And that is because your assignment for today and your Monday daily assignment have to do with calculating density, volume, and mass. So both of them are pretty short and straightforward. I think 5 or 6 questions each. And all you have to do is solve the problem for whatever it is that it is asking for. So it gives you a little bit of a quick example of a density problem, just to kind of remind you of our density equation, mass divided by volume. And so for the first couple of problems, that's exactly what you're going to do. You'll be given the mass and the volume of something and asked to find the density. You'll get the mass and the volume of a block of wood and asked to find the density. Number 3 changes it up a little bit. It gives you the density of a substance and its volume and asks you to find the mass. So I give you a little bit of a hint of what the mass equation looks like. And then number 4 changes it up a little bit again. It gives you the mass and the density and wants you to figure out the volume. And once again, I gave you a little bit of a help with a reminder of the volume equation right here. And then finally, for this homework, 5 and 6 go together. So number 5 gives you a rectangular block. It tells you the mass, but it doesn't give you the volume directly. Instead, it gives you the dimensions of this rectangular block. Luckily, since it is just a basic rectangular kind of prism, it's pretty easy to calculate the volume of the block. All you have to do is the width times the height times the length. So number 5, the answer will be whatever the volume of the block is right here. And then for number 6, you'll use the density, or excuse me, you'll use the mass that number 5 gives you and the volume that you calculated in order to figure out what the density of the block is. So for number 6, you'll use 2 numbers from number 5, the one that it gives you and the one that you find out on your own. So that is today's daily assignment. Pretty straightforward for most of those questions. And then when week 7 rolls around on Monday, let's see, where's week 7? It's a bunch of similar type questions. The numbers are a teeny bit more complex. You're just having to deal with some decimal places now that you didn't have to before. But the other thing is make sure that you pay close attention to the values that you have. And what I mean by that is that don't just see, oh, we have 5 and we have 96.5, so I'm going to do 5 divided by 96. Because if you read it, it mentions that the mass is 96, which means 5 centimeters cubed is a volume. So you have to do mass divided by volume in order to find your density. Similar thing with number 2, it gives you a mass of wood and it gives you a volume of wood, asks you to calculate the density. Number 3 mixes it up again a little bit. We have a density of sugar and it wants to know the volume, so it's asking what is the volume of 7.85 grams, which is a measurement of mass, right? Grams is mass. Number 4 similarly gives you the density and wants you to figure out what the mass is if the volume is 1.5. And then finally, number 5 is a little bit different from all of them that we've been talking about so far. Number 5 says silver has a density of 10.5 and aluminum has a density of 2.7. If you have a 2 by 2 by 2 cube with this mass, is that cube made of aluminum or made of silver? So you have to figure out the volume, do the density equation with your volume and your mass, and then see, does that density most closely match my aluminum density or my silver density? And that's what you'll choose for your answer. Based on the density, is this thing aluminum or is it silver? So again, this is the assignment that'll be coming up on Monday. So it's a good way to kind of review some of these basic density equations that we've been talking about tonight. All righty. Does anybody have any final questions about what density is, how to calculate it, how it's related between different matters?
No, sir.
I don't, but can